non-commutative computations.
Okay, thank you very much for the invitation. So, yes, let's start right away. Basically, I'm going to be talking a little bit about the non-commutative setting and then some things a bit different afterwards. But the main question comes from the results that we have on algebraic branching programs. And this is mainly this really beautiful result from Nissan, which gets an exact characterization of the complexity for non-commutative algebraic branching programs. And there's been some work in non-commutative computation over the years. This is obviously not an exhaustive list. Afterwards, I just mentioned this because for me it was always a kind of a surprise that this extremely simple result did not have that many extensions for a while. And that's why I was quite happy to be able to get some different kinds of extensions and generalization. And this, especially the last one, also gave an extension of the characterization. So some stronger types of models where we can pinpoint exactly the complexity. You give me a polynomial, I look at some rank, some object, some matrix, and I say, okay, the smallest size of the whatever model computing it is this exactly. And what I want to talk about today is not something that I'm involved in, but it is the fact that recently some colleagues in Paris, they show how you can get these results from known results on formal series. So in a way, it's interesting to see that even Nissan's results goes back much further. There's a much older result that basically gives everything. And then that you have an extension of these older results to formal series that are not on words but on trees. And these, with some work, and that's what they do here, is the work, will give you basically what we had there. So it's kind of nice. What I will not do is actually talk about what they do. What I want to do is really go back to the old results, which have a more algebraic flavor and presentation. Because if you go look at their, so it's on Archive, I think, or whichever of the preprint servers, because they address an algebraic complexity audience, they write it again in the language of circuits and stuff like that. But I want to do the presentation in the original language, basically, where the flavor is more algebraic. So just to start, I'm sure everybody knows what an ABP is and Nissan's result, but just very quickly. So you have this layered graph. You have linear combinations of the variables on the edges. The weight of the path is the product, and then you sum the weights of all the paths, and this gives you your computational model. And in Nissan's case, you have a nice layered ABP because you're only interested in computing homogeneous polynomials, and we'll come back to that. Okay. And what is Nissan's result? Well, he says, okay, I'm going to cut my position. It's not commutative, and it's homogeneous of degree D, so I can really see monomials with positions, and I'm going to cut positions, let's say, at position k, write all the possible monomials of degree k, all possible monomials of degree d minus k, and in this matrix, I'll put the coefficient of the polynomial I'm interested in. So I have a line for every monomial of degree k, a column for every monomial of degree d minus k. And then I look at the rank of this matrix, and it gives me some kind of complexity measure. And then if I sum actually all the ranks of these matrices, then I get the size of the smallest homogeneous algebraic branching program for my polynomial. So I get my exact characterization. And obviously, then if you do a short computation for the permanent, then you can get a lower bound. Okay. Incidentally, that was, we were talking about this yesterday. If you do this for the determinant, Murinal said it was not clear that you had some non-trivial multilinear computation of the determinant, but the same computation, Nissan gives you an algorithm for the determinant with the same from Nissan's paper, basically.
Lower bound, not a...
No, computation. It's a characterization.
Yeah, that's fine.
Yeah. So you actually get you really get the same exact computation. Okay, so we switch and we go to formal series on words. Okay. So what do we okay, so I'm gonna use a book by Burstall and Rottenauer as my basis for the talk. And if you use the book, things are more complicated in the way I'm going to show them because they do things more generally. So instead of walking over a field, they'll work over a semi-ring or something like that, so things get kind of hairy, but we'll stay with the field, so everything is really extremely simple, actually. So you fix a field, and you have a finite alphabet, and you look at finite words, and a formal series is just a function from the finite words to your field. And I'll use the usual notation in this domain. Actually, Wikipedia says that this is idiosyncratic. I don't know why, but that's the way that it's written. So the coefficient of a given word in the series is noted this way, so you can rewrite the series in this way. And there's this notation for the set of formal series. It's easy to define the support, and if you have finite support, you call this polynomials, and you get the set of non-commutative polynomials because your words are inherently non-commutative objects, if you want. Okay. And now we'll isolate a certain subset of the formal series that we call recognizable, and for this we'll say that we have a linear representation, and what it is, we'll need some dimension, some integer. So we'll be actually, so here it's the matrices, but basically it's kind of like, in a way, we're over k to the n, so the vector space. So we have a finite dimensional vector space. You could have written it this way. And you have a morphism of monoids from the words to the set of matrices, and two extra vectors, line and column. And what you want for it to represent a certain formal series is that the coefficient of a word is expressed as this. So this is a matrix product. So you'll have a line, matrix, column, and then it gives you just a coefficient. Okay? And obviously, to define a morphism of monoids, you just need to define mu over all the letters in your alphabet. And then by the monoid property, the morphism property, it extends to all finite words. Okay? So this is called a linear representation. N is a dimension. And it is, maybe not obviously, but it is an automaton. So maybe I should nevertheless make a small drawing, basically. What are you saying? You are saying that you look at the words, and this, as an extension of your mu a's, each mu a gives you some kind of matrix. And so you have, let's say, 1 to n, which are the states of your automaton. And for a given letter a, you have some coefficient, so let's say mu a ig, that says you can go from I to j. And if you put them all and write them like this, and then you add an extra, two extras, this is input and this is output, and this will be the lambdas, okay, lambda I, and this will be the gamma, thank you. I was thinking mu is not a good idea, it's the other notation, okay. Then basically as an automaton, the coefficient of a word in your series will be the sum of all the ways of getting the word going from input to output, basically. Okay. So obviously what happens is that inside here, you could have loops, cycles. There is no, this is for formal series, support is not necessarily finite, so you can have cycles in there. And now we want to characterize recognizable series. So, it's easy to see that you have a vector space structure, and we'll define this construction. You take a word, and you look at u minus 1s, and the easiest way to see what it is that the coefficient of a certain word in this new series is just the coefficient in the old series of the word uw. Okay? In other words, you take everything in S that starts with u, everything else you throw it away. You take everything that starts with u, you factorize u, and what you have in your parenthesis is your new u minus 1s. And a subset of formal series will be called stable. Well, when I use this operation, I stay there. Okay. And now you have these three really, okay, so I put these names here. It's not completely clear that the history is this way, but with my presentation, so I wanted to quote them because it's the oldest result that kind of imply this, but it's not completely clear the linear history. But a formal series is recognizable if there is a finite dimensional linear subspace that is stable and contains my formal series. Okay, so what I want to do, even though I don't have a lot of time, I want to give a proof of this. And it's not because the proof is really illuminating, it's more because it's yes?
Why isn't the whole space a linear space which contains S and is stable? Just the space of all formal series.
No, this is the space of all formal series.
Yes, so
not all.
If M is everything.
Yes, but it's not finite.
Oh, finite M.
Yes.
Okay, very good.
Okay. So it's not that the proof is particularly illuminating, I think, but I think it's particularly simple, and I want to stress this in a way. If you are, at least if you stay working over field, this proof is very simple. So I will do it, not too slowly because I want to talk about other things, but I want to show this. So there's two ways. You want to say if it's recognizable, then I get this linear subspace. If I have the linear subspace, then it's recognizable. So suppose you have it's recognizable, so you have a linear representation. Then you'll start by defining your generator set that you want for your finite dimensional stable subset that contains S. And it'll just be defined in this way so that it's clear that S is a linear combination. You remember S had the coefficient of a word for S had to be given by this matrix product. And you can just slice it by index. And it gives you that it's a linear combination of the SI that you've defined here, basically. So this, you get it for the containment. The finite dimension is because you've defined just a finite number of them. And the stability is just a computation that is only relies on the morphism mu, basically. Okay, so I'll just skip it. You can do it. And the other way is maybe just a little bit, it takes just a little bit more time, but suppose that you have such a finite dimensional subset that contains S and that is stable. So you say that it's generated by some formal series S1 to Sn. And then what you want to do is define this mu, this morphism of monoids, over all the letters of your finite alphabet. And you'll do this by saying, okay, if I take this series for one of my generators, I know that it's in my set M. Therefore, it is itself a linear combination of my generators. And I use this to define my coefficients, basically. I will call these alpha j, forget them. Now I just call them mu a I j. And this defines my the matrices I needed. And then there's a small computation where I think here there's a step where you actually need a few extra lines to write on the side. But
Guillaume, question. There's
yes.
a theorem on linearly current sequences. Is this the special case when the alphabet?
I have no idea.
I had the impression this is if the alphabet has just one element, so you're looking at formal power series.
Yes.
And there is a theorem on linearly current sequences when you can express it as a fraction, the generating function. I have the feeling this is this.
I really don't know, but yeah.
It's very much the same.
It seems also very similar to eliminating division from a computation of a polynomial in that, where you cut it by the degree of the output.
Yes,
it's the same. You have a recurrence.
It's also a very classical thing in automata theory that you look at the quotients that you can create, and that gives you basically the sets, the states of some automaton or things like that when you have a language and things like that. So
the point is that it is illuminating, I think. There is a simple intuition behind it.
And then, so there's a computation that I will skip, but everything works, okay? So just with this small result, you can see that also there's a kind of tight relationship between the dimension of the representation and dimension of the linear subspace. And just for example, even though that's actually so there's this, where did the names go? Anyway, yes, here. So there's this lemma, and it's proved the same way, in a way, by Arvin et al. Because they look at the rank of with Nissan's result, basically. But here, it's an old theorem also, and it's completely obvious. If you have generators for S and T, then if you look at the Hadamard product, and Arvin will talk about it also tomorrow, I think, which is defined as just taking the product of the coefficient, coefficient by coefficient. Then if you have recognizable series, then also the Hadamard product. And if you apply this, I haven't talked about polynomials yet, finite support, things like that. But if you apply it, if you believe me and it works for polynomials and finite support, then you just get this, and at this level, it's completely clear. That's why I kind of like it at this algebraic level. So now, yes, okay, we were talking about formal series, but what happens okay, not yet, for polynomials. Okay, now, the previous result, actually, it's, in a way, you say, okay, if there exists a subset that's stable, okay, so why not look at the smallest one? Which means why not look at everything that's generated by these series, basically. And then if you do that, you can start to see what's happening in your, basically in Nissen's matrices and what will be called the Henkel matrices. You look at the dimension of the space generated by these guys, and you get that this dimension is the smallest dimension if it's finite of a linear representation, size of the smallest automaton, and this is what is called the Henkel matrix. So before, in a way, you were saying, okay, if I have u and v and I put the coefficient of alpha uv and I get my matrix, and it means that this line is just u minus 1s, this quotient, and when I look at the rank of this matrix, I'm just really looking at the rank of this minimal stable linear subset that contains the S. Okay. So now, if you go back to ABPs, that's what I was thinking of. You have an exact characterization of complexity if you just use your automatas as a computational model. And the problem is that there may be cycles, and they have an observation that if the polynomial is homogeneous, then a minimal automaton is an ABP. Actually, the here is not, I mean, I wanted to write, and that's on the next slide, actually, I think. Any minimal automaton that you get from the Henkel matrix will actually be acyclic. It doesn't matter on the choice you make. This can be seen, maybe I'll skip this. This can be seen because of the way you define your matrix, but I'll skip this. It can be seen better here, is that basically you'll be expressing certain polynomials of a certain degree as linear combinations of other polynomials of degrees that can be of different degrees. But since you have a kind of block matrix, if your polynomial is homogeneous, you cannot complete some monomial with something that is too small or too big, etc. Okay? So what about non-homogeneous polynomials? So what I just said is that if it's homogeneous, all minimal automata obtained from the Henkel matrix are ABPs. They are acyclic. So what is your intuition? If I give you a non-homogeneous polynomial, do you think that having loops in the ABP, can it help you compute it faster or not? I see a no. So yes, this is true, but it's not true that all minimal automata will be acyclic. So this is a little thing that I can add for you for the talk today. But first we have a small challenge. Give me the smallest ABP you can find for this polynomial. I'll write it here. What can I do? I can do this with A plus B, B. And it's true that I won't be able to find smaller with loops, but can you find one that has the same size with loops? I said not all minimal automatons can use loops. Can you compute this very simple polynomial with loops? And you can check that if you do this, so I hope I won't make a mistake. A, B, B, minus B, minus B, and this is output and this is input, then it computes the same thing. So, can we always have one that is really an ABP? Well, yes, oops, okay. So this is something that actually you can do. It's not very, very hard to see. There exists a minimal automaton defined from the matrix, which is acyclic, and then it means you get a slight generalization of distance result. In general, the ABP complexity of a polynomial is the rank of the Henkel matrix, whether it be homogeneous or not. So it won't be exactly the same kind of layered ABPs as in Nissen's, where the arrows go just from one level to the other, but it'll be, we'll have a shape that is similar. Okay, so I'm going to go very fast for the rest of the talk, but the rest of the talk has no technical details. So now let's look at formal series on trees. I will stay in the general, more algebraic setting, and this means that now I have a finite ranked alphabet. It means I have symbol with arities. So sigma is a union of sigma k, and sigma k is a symbol that will take k arguments if you want. So sigma 0 is my letters, my A from last time. And now you consider trees over sigma. It means that if I have I didn't write it here, but if you, as usual when you define trees, a tree is either an element of sigma 0 or it's obtained by applying a symbol of arity k to k trees that I've already obtained, okay? And this gives us, as my undergrad teacher would call it, the free magma over sigma, but I think this is a French terminology. Yeah, it goes well with solar methods and galactic things. But so I think it's really French. But we really are taught this way. I don't know why. And the formal series is just a function from trees. Just think trees over your alphabet to k. You have all the same definition and polynomials with these weird symbols objects. Okay. And now you will get also a notion of recognizability. And also via some mapping, but it gets a little bit. So for each symbol, you need some k-linear map. So it's I will go quickly. The point is not so much of really understanding what happens. And you also can characterize in a way the same kind of results, formal series that are recognizable. So these are really formal series over trees. So what does it tell us for us? What is interesting? Okay, yeah, this I will skip. You also have an idea of a Henkel matrix with context. I will skip basically all this because I don't have a lot of time. But let's just look at the case where you only have variables, sigma 0, and then you have just one symbol of arity2. So you are really looking at binary trees over your variables. So you are looking at monomials that are non-commutative and non-associative. Okay? And so your formal series are non-commutative non-associative series, and if the support is finite, you are looking at polynomials, but you are now in the case where they are non-associative, non-commutative. And then you get everything else. So this is also what they notice is that basically in that case, the automaton can be seen as circuits if they are acyclic, and you get the same kind of characterization. So which means that you get, again, the fact that you perfectly understand the complexity of computing non-associative, non-commutative polynomial, which in a way is not a huge surprise. I'm telling you, you're computing this polynomial, and each monomial I'll tell you exactly the computational structure, in a way, the associative structure. And then it's not a surprise, but it's not obvious, but it's not a surprise. Well, then you can say exactly what is the smallest way to get this. Okay? So again, it's possible to see that in the case of non-homogeneous polynomials, they will not all minimal automata that you get from the Henkel matrix are acyclic, but there will be a choice of minimal automata which is acyclic, which will give you a circuit in this case. Okay. This I will skip too. So I just want to get to this conclusion. So we understand perfectly what happens for non-associative, non-commutative polynomials. So one question could be, can I use this? Okay, I want to show lower bounds for, the open question. We don't have better lower bounds for general non-commutative circuits than the just general lower bounds for circuits. So can I use this to get lower bounds for non-commutative circuits? What would I need to do? Basically, any non-commutative computation, I can see it as being non-associative. I can write the Henkel matrix. I can look at it. But I'm not replacing, I don't get a good measure. I'm not replacing my quest for lower bound with a measure that says, okay, now I don't have to think about to show that there doesn't exist small circuits or whatever. Here, you are going from does there exist a small circuit to does there exist some way of writing the Henkel matrix such that as when I identify non-associative monomials and project them down to their associative version, it gives me the polynomial I'm interested in. So there's still this kind of ill exists. You are still search space over possible expression of your Henkel matrix of a given monomial. So it's not clear that it helps really a lot, but it's still some way of looking at it. Basically, you get that you have some linear constraints on the coefficient of a matrix, and you want to lower bound the rank of a matrix under some linear constraints that you can write explicitly, but that still does not help you, at least for the moment. One other reason why this might not be a fruitful angle of attack for this problem is that actually they also notice something very fun, but is that actually you can take away the non-commutative part. So you also get an exact characterization of circuit complexity just for non-associativity. This is very strange, but it actually completely works. It's not, I can do a lot of things and make it work. No, it's exactly, you just define your trees as unordered instead of ordered, and the whole process works exactly the same. There is no difference. Okay? So this means that if you can do something too clever here, and it might be possible to do it here, and then, I mean, it doesn't mean that it's not going to work, but then you get general lower bounds, and I don't think it's going to be with these small Hankel matrix things that you're going to get lower bounds for general circuits. So, okay, I think I'm going to stop there.
Question. Is there any characterization they get for ABPs or formulas or something in non-associative?
I'm sorry? For
so for circuits they give this characterization.
Yes.
For other models also, do they have some characterization?
No, that's a very good question. So it's hard to get something for, I would like to have a characterization for formulas. It's difficult because you see that this is, it's what I said. It's basically say, just you get your information only from the structure, the non-associative structure of your monomials. And a formula is something that is just about the computational model, but doesn't change I mean, it will give you some things on the way you build your monomials, but if you take a circuit and you spread it as a formula, it will give the same associative structure. So it's hard to find. You could also say, okay, I'm going to look at Hankel matrices where what I write in the matrix, I skipped everything, so it's not clear, but I know that I can parallelize them, for example. So maybe I will look at Hankel matrices where I restrict the trees that I write to be of log depth, but this will not help you separate from branching programs, because branching program can also be parallelized. So I would like a characterization of formula size in this context. That's something I would really like.
Other questions? Thanks.